Hi, it's time for another math easy solution. Today I'm going to go over further into infinite series and sequences. And now let's look at the comparison test. And again, I'm just following along my calculus book. And note, like always, if you don't have time to watch this whole video, because it's going to be pretty long, so you can there's no summary conclusions in this video, but you can play this video at a faster speed. And this is my recommendations. It's pretty much like a life hack. And also, you can download and read the notes, and you can read the notes on Steemit in article format. The link will be in the description below, and you can watch the video in parts. It doesn't need to be all at once. Alright, let's just dive right in. So just calculus book reference. Just note that I mainly follow along the following calculus book, especially in this video as well. So Calculus Early Transcendentals, 6th edition by James Stewart. Alright, so let's get further. So topics to cover. I'm going to go over introduction to the comparison test, the comparison test, example 1, note number 1, then example 2, then another note number 2, and then a limit comparison test, go over another couple examples, example 3 and 4, and then estimating sums, and go over an example on that, and then go over some exercises that develop the skills we learned here, or the concepts, into more in-depth problems. And that's four exercises, exercise 1, 2, 3, and 4. So let's go further. So introduction to the comparison test. So in comparison test, the idea is to compare a given series with a series that is known to be convergent or divergent. For instance, the series, if you were to draw this one from the summation from n equals 1 to infinity of 1 over 2n plus 1. Yeah, so this series is very similar to this one right here. So it reminds us of the series summation from n equals 1 to infinity of 1 over 2n. So just remove that 1 there. So yes, I'll just write is similar, just to make it just to appear in the same written path right here. So it's similar to just removing that 1. So n equals 1 of 1 over 2n, and this is a geometric series right here. So this right here, summation of from n equals 1 to infinity of 1 over 2n, so that series, which is a geometric series with a equals 1 over 1/2 and r equals 1/2 of the ratio, and is therefore convergent. And again, recall the geometric series from an earlier video on infinite series. There's a link there. I need a screenshot from my calculus book, just gets more compact. So the geometric series, summation from n equals 1 to infinity of ar to the power of n minus 1 equals to a, and then a plus ar plus ar squared, and so on. So this one here is ar 0, because the first term n minus, when n is equal to 1, you'll have 1 minus 1 is 0. So just r multiplied everywhere there, starting from r0. And then it squares, and then it goes r3, and so on. And it's convergent if the absolute value of r is less than 1. So again, recall there, prove it in that video. And its sum is right here. In the sum, you can get an exact sum. It's going to be a divided by 1 minus r if it's convergent. In other words, absolute value of r is less than 1. But if it's the absolute value of r, the ratio is greater than 1, greater than or equal to 1, the geometric series is divergent. And here, just to recap even further, so I'll show you that this is a geometric series. So I'll just write thus: if we have the summation right here, infinity n equals 1 of 1 over 2n. If you were to sum this up, this is when you put 1 in there, you're going to get 1 over 2 plus. Then you put another term. So the second term is going to be 1 over. This is 2 to the power of 1. It's 2 to the power of 2. And then plus 1 over 2 to the power of 3, plus so on, and then it goes to, spread one more, 1 over 2 to the 4, plus dot dot dot, it keeps going on, and this one just equals to, well, this is going to be 1/2, plus here is going to be just a 1/2 times it by a 1/2. Then here's going to be a 1/2 times it by a 1 to the power of 2, and then a 1 over 2 to the power of 2. Let's just take that 1/2 there. So in other words, this is their a there. Then one last one, plus 1/2, then 1 over 2 to the 3, and so on. Yeah, so in other words, this 1 over 2 to the power of 4 is the same thing as writing 1 over 2 times 1 over 2 to the power of 3. So yeah, because the powers, they can add up. And then this one just equals to, well, a, that's just our 1/2, plus, now we have a times it by r, so there's the a, and then there is the r like that. This one right here is a, again, times it by right here is r squared. This is just r squared. like that. And then likewise going one further, so we have again a times it by this r cubed plus dot dot dot. So in other words, we have a geometric series, and this one again you can see this as is r1, this r0, like that. Yeah, so thus for completeness, just to recap further, so thus we will have the summation infinity n equals 1 of 1 over 2n. This just equals to the summation from n equals 1 to infinity, and this one's going to be, well, a is 1/2 times it by, well, now we have a 1/2 and then the power of 0 here. That's because we'll have n minus 1. So if it's n is 2, we'll have 1. So in other words, this is going to be to the power of, let's put it like this, n minus 1. So in other words, this just equals 2 summation infinity n equals 1 over 1 a times r n minus 1. So we have a geometric series, and this is a geometric series. Yeah, geometric series. And in this case, we have r equals to a, and they're both 1/2. Or I'll just write it like this. A equals to r. No, I mean a equals to 1/2, and r equals to 1/2, which is less than 1. So it's in other words, it's convergent. So the absolute value is less than 1. It's positive, so it's just going to be less than 1 over there. So it's convergent. Alright, so so I just wanted to go over that, just to recap, mainly for myself. So now, because the series is so similar to a convergent series, so right here, this is very similar to this one right here. So this 1 over 2n plus 1, this one was just 1 over 2n. So all it has is an extra 1 there, which it shouldn't change anything. So we have the feeling that it too must be a convergent series, and indeed it is. So yes, if it's similar to a convergent series, then we suspect it is. So in other words, going further, the inequality right here, 1 over 2n plus 2n plus 1. Let's see, plus 1's here. This is always going to be greater than, actually. I mean less than, So you're dividing by a bigger number. So you had this extra plus 1. So it's also going to be less than just 1 over 2n for any of the subintervals or any of the terms. Yeah, because you're always going to be dividing by just one extra integer larger. So yes, it's going to be a smaller number when you divide by a larger number. So yes, this inequality shows that our given series has smaller terms than those of the geometric series, and therefore all its partial sums are smaller than 1, the sum of the geometric series. So when you combine all of the partial sums, any of the partial sums is going to be less than 1, and then the actual sum is the partial sum as it goes to infinity. So, and this is going to be equal to 1. I'll calculate this right here, but you can see here from my earlier video, I showed that it's equal to a over 1 minus r is going to be the sum of the geometric series. So thus, or I'll just write note to show you that it's equal to 1. So note that the geometric series from n equals 1 to infinity of a r n minus 1, this equals to a over 1 minus r. And in our case, we have both of them as 1/2, so we're going to have a 1/2 divided by a 1 minus 1/2. In other words, this one right here, so 1/2, and then this one's 1 over 1 minus 1/2. That's the same thing as writing 2 over 2, so 2 minus 1 is 1. So we're going to get a 1/2. So we're going to get a 1/2 on the top over a 1/2. They cancel, you're going to get equals to 1. So in other words, the summation right here, this is the geometric series, infinity n equals to 1 up to infinity of 1 over 2n is equal to 1. So that's the sum. Yeah, so it should be less than it. Yeah, so then this one should be less than that, so it should also be convergent. So yes, this means that its partial sums form a bounded increasing sequence. And it's an increasing sequence because this one right here, it's always positive. You're never going to have a negative number right here. There's just 2 to the power of positive number, because the terms are from positive 1 to infinity. So then you're always going to be positive. So you're always going to be increasing that sequence. You're always going to be adding to it, which is convergent. Because it's increasing and it's bounded, it's always going to be less than this one there. So it also follows that the sum of the series is less than the sum of the geometric series. So we'll just put this like this. Infinity n equals to 1 of 1 over 2n plus 1 is less than 1. Like that. And yeah, similar reasoning can be used to prove the following test, which applies only to series whose terms are positive. So the first part says that if we have a series whose terms are smaller than those of a known convergent series, then our series is also convergent. The second part says that if we start with a series whose terms are larger than those of a known divergent series, then it too is divergent. So yes, it would be the counter version of this one right here that we just saw. So the comparison test. Suppose that the series an, or the summation of the sequence an, and this one right here, sum of bn, are series with positive terms. So yeah, assuming they're positive, so yes, they're always going to be increasing, because you're always going to be adding positive terms. So if the series bn, or the summation of b sub n, is convergent, and an is less than bn, the sequence for all n, then the summation an is also convergent. So yes, if the terms are smaller than the terms of the convergent series, then it is also convergent. But and vice versa, if the summation of bn, or the series right here, is divergent, and an is greater than bn, or the terms or the sequence an is greater than bn for each of these intervals there, or terms, for all n, then this is also, then the series an is also divergent. So yes, basically if the terms are greater than a divergent series, then it is also divergent. Proof. Firstly, it is important to keep in mind the distinction between a sequence and series, as I've pointed out before. A sequence is a list of numbers, whereas a series is a sum. So yes, a sum of those list of numbers, for example here. So an is a sequence, and then the summation of an is the series. So yes, series, and then you have sequence. So the sequence inside, and the total is a series. And yeah, further, so with every series right here, summation of an, there are associated two sequences: the sequence an of terms, and the sequence sn of partial sums. So yes, which is the sum of the terms when you add up all the terms up to n, which is it could be 10, 20, and so on. If it goes to infinity, that's the total sum. Alright, so now that I got that out of the way, I just want to now let's look at the proof for the first part of this comparison test, which is the series bn if it's convergent, and then the sequence an is less than bn for all n. In other words, all the terms of an are less than bn. Then also the series a sub n is also convergent. So what I'm going to do now is I'm going to write here, let's look at I, and I'm going to do is I'm going to let just define some terms. I'm going to call s sub n, or sn, as equaling to the summation from I equals 1, because we have n there, so we just use a different term. So we'll have now a sub I, and then up to n, like that. So this is just the partial sum of the sequence an. So when you sum it all the way up, or the series partial sum of the series an right here. Again, we just use different notation there, I, because there's an n there. So now define that, and then what I'm going to do now is I'm going to define t sub n equals to the same thing, but for the other series or sequence. So bi, I equals 1 up to n. And then lastly, what I'm going to do is, because we know that the bn is convergent, so we know that this series is convergent. This is just a partial sum, we'll call it t. So this one's s, this is for the a, this one is t for the b. So it's convergent. So in other words, when we take it to infinity, it's going to go to a specific value. So I'm going to call that t. This just equals to the summation I'm going to call this n, equals to 1 of bn up to infinity. Sum it up, this equals to t, like that. So that's what I'm going to let this equal to. And this one, again, this is just different notation. This just equals to the limit as n approaches infinity of this this partial sum, like that. So I'm going to call this like this, of n. This is I equals 1, goes all the way to n, where n is approaching infinity, of bi. So this is just same thing, like that. Yeah, so yes, just write this down. This is convergent, this one right here. Just put this t. So we have a t as a number because this is convergent, like that. And what we got to do is prove that this is convergent. So basically prove that this is s and question mark, like that. Or I'll just write it down here. Prove that Sn equals to S is also convergent. Yeah, so basically prove that like that. Or I just better put it as a question. Does this mean Sn equals S and that is just a number? 2, like that. And the answer is obviously yes, as we'll prove, and that's part of the comparison test. Alright, so going further in the proof, so since both series have positive terms, the sequence or the partial sums, the sequence Sn and Tn are increasing. In other words, what we have is, well, if you add another or go to the next partial sum, so Sn plus 1 is going to be equal to, well, just Sn plus the next term in the sequence An plus 1. And this is going to be, yeah, so this has positive terms, because that's what we're given. This is going to be just increasing by a positive number, so it's going to be, well, greater than or equal to Sn. So it's always increasing. So it's always, the next one's always going to be bigger. Likewise for Tn plus 1, this just equals to Tn plus the next term, which is going to be b of n plus 1, like that. And this is going to be greater than greater than Tn. So this is also increasing. All right, so going further, also what we know is also, let's write also like here. So this one right here, t, is in other words, this is our Tn there. So in other words, this just equals to the limit as n approaches infinity of the partial sum of like, or actually not the partial sum, just Tn. Yeah, so this is just, this right here is Tn. So basically, yeah, the limit as this whole thing, this is just that. This is approaching t. So also Tn is approaching t as n approaches infinity. So thus what we have is thus Tn is going to be less than or equal to t for all n. Like that. So yeah, so this is bounded. It's always going to be less than this number t, like that, because we know it's convergent. And since we're given that each term, so remember the comparison test, so we're given that if Bn is convergent, and then also the terms An is less than Bn for all n. In other words, each term is less than it. And in our case right here, since so we have the partial sum Sn, we're just going to look at Ai. Yeah, so this Ai is the same thing as An less than Bn. We're just going to write Ai is less than Bi. So each term Ai is less than or equal to Bi, like that. Yeah, so each term is less than the comparison term, or the comparison term, or comparison sequence term. So that's what we have is, let's write this better, I. So what we're going to have is Sn is going to be less than or equal to Tn. Yeah, so essentially we're just putting into just more general terms exactly what we showed in the previous geometric series example. So what we have is, so thus what we have. Yeah, so thus Sn right here is, it's less than or equal to Tn, which is, well, this is going to be less than or equal to t, like that, because it's because it's bounded there. So in other words, Sn is going to be less than or equal to t. So this is bounded. It's going to be approaching a number or less than this. It's not going to get greater than that. And I'll just write for all n. I'll just highlight this because that's pretty much the proof. So yes, this means that the partial sums Sn, sequence of it is increasing and bounded above. So in other words, it can't get higher than that number t, and therefore converges by the monotonic sequence theorem, which I went over in my earlier video. Thus, we have the series An converges. So recall the monotonic sequence theorem from my earlier video on infinite sequences, and this one, here's a link to it, a steamed one, and again, screenshot from the calculus book because it's more compact. So just recaps the definition, sequence An is called increasing if we have the next term is always greater than the first one, or the previous one. So the next one's always bigger than the previous one, so you always have the terms bigger and bigger and bigger, and is called decreasing if we have it smaller than the previous one for all n it's greater than or equal to 1. In our case, we have it the partial sums increasing because the terms are positive, so you're always adding more and more into it. It is called monotonic if it is either increasing or decreasing. So yes, that's where, so ours is monotonic. And then recall the definition of An is bounded above if there is a number m such that An is always less than or equal to m for all n greater than 1, and it is bounded below if there's a number lowercase m such that m is less than or equal to An for all n, like that. So in other words, it's below it. But ours is going to be bounded above. So this is where ours is going to be less than RT, and it's always increasing. So we have this, it's a monotonic sequence. So we have a monotonic sequence, it's always bounded above, and again, you can see more detail on this in my earlier video. And then if it is bounded above and below, then it is a bounded sequence. So monotonic sequence theorem, every bounded monotonic sequence is convergent. And again, essentially, if a sequence is always increasing, like that, or decreasing, hence monotonic, it is bounded above or below. Then it will approach a number or limit L, which is less than or equal to m, in our case t, or L is greater than or equal to lowercase m, if the sequence is decreasing. So for example here, so ours is going to be our t value there. So that's going to be our t, and notice how the sequence is always increasing, so the partial sum is always increasing, and it's going to be less than or equal to this one, so this L could equal that, but it can't go anywhere bigger. So in other words, it's converging. So yeah, it's converging to this point like that, or to that value. So yes, that is a monotonic sequence theorem. So this is a recap on that. So now let's look at the second part. Alright, so now let's look at the second part right here of that comparison test. So the second part says, again, if this is divergent, if the the series Bn is divergent, then and we're given that the sequence An is greater than this Bn for all n, then, or the terms are always bigger than the comparison term, the Bn one, then the series An is also divergent. So what we have here, so recall this one right here, Tn equals to the summation from I equals 1 to n of B sub I, like that. So now, yeah, if this is divergent, it's not going to equal to t, it's going to go to infinity. So what we have is, yeah, right here, so if the series Bn is divergent, then Tn approaches infinity, and not Ts, since Tn is increasing. This is right here, it's always increasing, the partial sum, because it's always positive terms. So in other words, what we have is, recall, just scroll up here, so we have this part here, so instead of equaling this, it goes to infinity. So we have Tn equals to that, so I'll just write limit as n approaches infinity of Tn, this just equals to the limit as n approaches infinity of the summation. It's going to go n like that, I equals 1, and this is going to be of our Bi, this goes to L0. I mean infinity, not 0. So this goes to 0, I mean infinity, positive infinity, because this is always positive, and it's always increasing. Yeah, because this is positive terms, we're always adding more and more positive terms. It's going to be increasing, it's going to be positive infinity there. Not 0. I don't know why I kept saying it. This is always going to go there, but we know that, opposite from the first part of the comparison test, instead of, yes, remember this one here, we have the terms less than, the A terms less than the B terms. Now we're going to have the opposite. We're going to have the A terms greater than the B terms. So what do we have here? But we have A sub I is greater than B sub I, like that. Or AN is greater than BN, and so on. But we're using the limits here, so we're going to use the I term like that. Yeah, so these terms are always bigger. So thus, what we have is, or better term, I'll just write so. So what we have is Sn, which is over here. So S sub n is equal to this summation right here, where these terms are always bigger than this term, and where this is approaching infinity. Thus, this is approaching infinity. Because, well, this is greater than the Tn. So we know that this is greater because the terms themselves are bigger. So it's always going to be bigger, but this one's going to infinity. Thus Sn is approaching infinity, and not a number. So this is approaching infinity as n approaches infinity. So this is approaching infinity as n approaches infinity, like that. Yeah, and therefore the series An diverges, because remember this one is just, Sn is just a partial sum of this sequence, like that, as you add them up at this An series. But yeah, up to n, again we use the notation I, because the n is already taken. Alright, so going further, so in using the comparison test, we must, of course, have some known series summation from, just Bn, like that, for the purpose of comparisons. We'll call this a comparison series. Most of the time, we use one of these series, and it's a P series, a summation, and recall my earlier videos, the P series is summation of 1 over n to the power of P, and this converges if P is greater than 1, so we know that. So if you know that, if P equals to 1, that's a harmonic series, and that's divergent. And diverges if P is less than or equal to P. And geometric series, which I discussed above earlier. The summation of AR to power of n minus 1, and it converges if the absolute value of R is less than 1, and diverges if absolute value of R is greater than or equal to 1. So again, I'll be using these throughout this video. So these are the standard series for use with the comparison test. Both the p-series and the geometric series are detailed in my earlier video on infinite series, again in the link above. Yes. So let's go further. Let's look at example 1. And this states, determine whether the following series converges or diverges. So this one we have is summation of n equals 1 to infinity of 5 over 2n squared plus 4n plus 3, like that. So again, this is looks all complicated, but what we know is we can compare it to, well, removing all these extra terms, 4n, look at the dominant one, dominant power, n squared there. So for large n, the dominant term in the denominator, let's look at the solution here, is 2 times n squared. So this is the dominant one over here, like that. So we compute the given series with the series right here. We'll just look at 5 over 2n squared. So look at the more dominant one as this goes to very, very large. And this can be much greater than here because you have an n squared term. Yeah, so first off, observe that if you compare this inequality or this terms inside. So we'll look at the full equation we're given. So 2n squared plus 4n plus 3. So this right here is going to be less than, well, just the dominant term. So 5 over 2n squared, because these are just extra positive terms because we have n equals 1 is all going to infinity. So these are always positive. 4n plus 3 is always positive. And you're going to be you're just adding a number at the denominator. In other words, you're dividing by a larger number. So this is going to be less than this right here. So it's less than, again, because the left side has a bigger denominator. And when you have a bigger denominator, you're dividing by a bigger number to get a smaller number. So in the notation of the comparison test, an is the left side and bn is the right side. So yes, we always had the an on the left side and the comparison one, bn on the right side. So we also know that, when we take this right here, this summation, just use the comparison series. So we'll look at is here. We know that summation n equals to 1 up to infinity of 5 over 2n squared. This just equals 2. We can just take out this 5 over 2 just because it's just a constant. So 5 over 2 factored out just using basic summation laws. N equals to 1 of infinity like this. And this is going to be 1 over n squared. This is just a p-series. So again, recall from my earlier video, this is just a p-series, and where it converges if p is greater than 1, and where p right here, so we have this is a p-series, like that. P-series where where 2 is, or p is equal to 2. P is equal to 2 and is greater than 1. So in other words, this is a converges, like that. Converges, let's write that, or convergent. Whichever one you want to write, converges. So I'll just write it down here. It's convergent because it's a constant, so we have 5 over 2 times a p-series with p equals 2, which is greater than 1. So that's convergent. So therefore, by the comparison test, we know that this is convergent, and this one's less than this one. Therefore, the entire sequence that we're given right here, infinity, n equals to 1, so the summation of 5 over 2n squared, and then this is going to be 4n plus 3, plus 4n plus 3, just write this, but need to put this in the middle. So therefore, this is convergent. And here, just wrote it down here. So it's convergent by part I, or part 1 of the comparison test. And again, scroll to the comparison test. It's just saying that if you have, if bn is convergent and an is less than bn for less than or equal to bn for all n, then then the series an is also convergent. That's exactly what we have here. So this is our an. The terms are less than the bn terms, and then we know that bn is just a p-series, so it's convergent. And so then this is convergent because its terms are less than a convergent series. So I'll also write a note here. So note number 1, although the condition an less than or equal to bn, or an is greater than or equal to bn in the comparison test is given for all n, we need to verify only that it holds for n which is greater than or equal to capital N, where n is some fixed integer. So it doesn't need to be for all n, just as long as it's greater than a number for all n greater than that. Yeah, because the convergence of a series is not affected by a finite number of terms. So yes, you need to go to infinity to verify it's convergent or not. This is illustrated in the next example. All right, and this example is right here, example 2. Test the following series for convergence or divergence, and we're given the sum from n equals 1 to infinity of ln of n divided by n right here. And obviously right here we could see a comparison. What we could do is 1 over n, which is the harmonic series, and that is where it's a p series of p equals to 1. So if p equals to 1, we'll have 1 over n, and that diverges. So we know that diverges, so what we'll do is try to get something like that. And this will make sense as I go through this. So note that this series was tested using the integral test in my earlier video on the integral test and estimate of sums. Here's a link to it, and there's a screenshot from my calculus book. So determine whether this series, the summation from n equals 1 to infinity of ln n over n converges or diverges. And then I made it into the function like this. Did the derivative. Yeah, took a derivative and then applied the integral test. Did some integrals. Got that it was infinity. Again, make sure to watch that for more detail. But it is also possible to test it by comparing it with the harmonic series, where p equals to 1, or the p series. It's a harmonic series. Yeah, special case of the p series where p equals to 1. So observe that ln n is greater than 1 for n is greater than 3. And the reason this is important is if it's greater than when n is greater than or equal to 3, and I'll show that it is, then what we'll end up having is a ln n, which is greater than 1, is going to be greater than a 1 over n, because we have an n there. So we have, this will be greater than the harmonic series. So what we'll do is first recall on inverse functions. So what we have is, the function y equals ln x. This just equals to, remember, log base ex, and what this is actually solving is just a power where the base is e. So this is basically solving this equation, x equals e to the y, like that. And also recall that e is equal to, it's equal to 2.718, and so on and so on. It's just a special number. Yeah, so thus what we have is, thus, if we want to know when ln x is greater than 1, so when y equals ln x is greater than 1, yeah, and this means that, well, I'll just write and, we can just take e to the power on both sides, so we can go e like this on all sides like that. We get, well, e to the y, this equals to e to the ln x, and this is greater than e to the 1. These are just using this property over there, and this just equals to x. Yeah, so e, so it's equal to e right there. So in other words, what we have is ln x, and here this is just a function, this is just a series with integer values, this one's all values. This is going to be greater than 1 for x is greater than this e, like that. And you can see here, right here, as you increase this greater than, as you make it e to the power of infinity like that, this goes to infinity as well. So yes, so and if you were to graph this out, just recall the graph. It's going to look something like this. X, this is ln x, and the graph looks something like this, where it's 0, and it goes to negative infinity like that. And this is our, this value right here is 1, and this value is 1 because, well, we know that e to the 0 equals to 1, like that. This is just by definition, most used definition for e to the 0, like that. And then at this point right here where this is 1, so I'll put something like this. So where this is 1, just make it the same scale. So then this goes all the way across here. So when y is 1, this equals to y. So what we have is right here is, at this point, is e. So this right here is like that, e to the 1, which equals to e is the x. So yeah, so when we're dealing with the inverse function, everything is switched around. So in other words, if we want to get greater than this value of 1 there, yeah, so if we want to get greater than it, we got to look at ln x is greater than 1 for x is greater than e. So basically we got to go all the way across here. Yeah, so x is greater than e, going all the way to the right of it. And in our case, for a series, because we're not dealing with a continuous function, a fully continuous function. And also make a note here. So this here, right here, this is approaching or the y is approaching negative infinity. So in other words, what we have is e to the negative infinity. This is just equals to 1 over e to the infinity. So this is approaching 0 for x. So that's where we have it going downwards like that. But for a series, so for a series, what we'll do is we'll choose, so instead of dealing with x is greater than e, we'll choose n has to be a whole integer, so n is going to be greater than or equal to 3. Thus, what we have is ln of n is going to be greater than 1, like that. If we chose n equals to 2, that's going to be somewhere across here, which is going to be less than it, so that's not going to work there. So that's what we have is, so thus we have is ln n over n. Yeah, ln n over n is going to be greater than 1 over n for n is greater than or equal to 3. So again, all we need to do is find an integer as this gets greater than it, and yeah, it doesn't need to be for all n below it. It's not a finite number, as long as this goes to infinity and this is greater than a number, like that. Where again, this is, so this right here, ln n is greater than 1. So we're going to have a number greater than 1 divided by n. It's going to be greater than 1 divided by n, like that. So yes, fascinating stuff. And again, we know that the harmonic series 1 over n, the summation of it, of 1 over n sequence is divergent because it's a p series with p equals to 1, again from my earlier video. Thus, the given series is divergent by the comparison test because this is larger than the terms, the terms of this is larger than the terms of a divergent series. Thus, the given series, ln n over n, is divergent by the comparison test, the second part of it. And also another note here, note number 2, the terms of the series being tested must be smaller than those of a convergent series or larger than those of a divergent series. So if the terms are larger than the terms of a convergent series or smaller than those of a divergent series, then the comparison test does not apply. Yeah, so consider, for instance, the series. We had, instead of the plus 1, we had infinity like this, n equals to 1 of 1 over 2n minus 1, instead of the plus 1, which we had earlier. Yeah, so if we have this, and then the comparison test, if we use the same one, we can't use it. Yeah, we can't use what we did earlier because the inequality, so I'll write 1 over 2n minus 1 is going to be, yes, this is going to be greater than 1 over 2n because you're going to be dividing by a smaller number. Denominator is smaller, that means it's a greater overall value. So it's going to be greater than this one, which is this is a convergent series, but this is greater than a convergent series, so it doesn't help us at all. So yes, this inequality is useless as far as the comparison test is concerned because the summation bn, or the series bn, equals to summation 1 over 2n. You have 1 over 2 power of n. Remember, this is a geometric series that's convergent because r is 1 over 2. Is convergent, and an is greater than bn. So it's, yeah, so this one's convergent, but this term is bigger than it. So we can't really use that series. Use that comparison test. But nonetheless, because this is just a minus 1, it should still be convergent because all we're doing is adding a tiny constant there. Nonetheless, we have the feeling that the summation 1 over 2n minus 1 ought to be convergent because it is very similar to the convergent geometric series summation of 1 over 2 to the power of n. In such cases, the following test can be used, and this is the limit comparison test. So let's look at this one. So suppose that the series an and bn are series with positive terms, so that the partial sum is always increasing. And I'm going to do now is if we have the limit, so limit as n approaches infinity of an over bn, so if we divide these out, if this equals to c, and the c, where c is a finite number and c is greater than 0, then either both series converge or both diverge. Yeah, so in other words, we could use this one now. So if we know if this is a constant c greater than 0, and bn converges, then an converges. If bn diverges, an diverges. So yes, this is just a comparison test, but now with this is the factor we gotta consider. And here's a proof for it. Let m, or lowercase m and capital case m, be positive numbers such that the number c is between them. So m is less than c, which is less than capital M. So because an over bn is close to c for large n, so this is the limit as you take n approaches infinity, it's approaching this number c. There is an integer n such that we have is going to be this c, so remember this is going to be b, it's going to be less than an over bn, which is our c, or approaches c as it goes infinity, less than m, like this. And this is when n is going to be greater than, or it's not greater than, or not equal to, just greater than n, like that. And again, the reason this is so is because this is the limit as n approaches infinity. So eventually it needs to get closer and closer to the c value. Yeah, so it's going to be approaching to it, it's going to be converging to it. So it's going to be greater than a lowercase m and a positive number at lowercase m, and it's going to be less than a positive positive uppercase capital M, like that, when n is greater than a certain point. Again, we're dealing with infinity, so eventually there's going to be a point where it's going to be converging in between these two values. Then eventually we'll be approaching c, the constant that we're given. So now that we have this one, and so what we could do is, and I'll write, and so I'm going to just multiply by b on both, bn on both sides, so we get a n times m, or put the m in front, just put m, bn less than, then this one will cancel out, we'll have an an, it's going to be less than bn capital M, like that. Or just put the m to the left of it, just because my calculus book does. Okay, and this is again when n is greater than capital N, so it's at a specific point, similar to the earlier example on ln n that we did. And now what we can do is apply the comparison test, the non-limit comparison test. So what we have here is this scenario. So if bn, or the series bn, converges, so does this, because this is just a constant times bn. So thus an converges. So if this converges, if what we're given is if this converges, then what we're going to be having is this converges. So if that converges, that's by the comparison test. So thus the series an converges by part 1 of the comparison test, because if it's comparing it now with a constant times this bn, where this converges at whenever n is greater than capital N, then what we have is the series an is convergent. And if this is divergent, so if bn diverges, so what we'll have is, well, an is greater than this divergent times it by a constant number. So in other words, we're going to have a constant number times a divergent limit or series, so thus this is going to be divergent. So if the series bn diverges, so does lowercase m times bn, this combined series. And part 2 of the comparison test, or part II of the comparison test, the non-limit one, shows that the series an diverges. So note that exercises 1 and 2 at the end of this video deal with the special cases where c equals 0 and c equals to infinity. I'll get to those at the end. So yes, fascinating stuff here. Alright, so let's go over example 3, which illustrates that same series that we were looking at. So test the following series for convergence or divergence. So solution, we could, this one right here, summation from n equals 1 to infinity of 1 over 2n minus 1. So we use the limit comparison test with, so here what we're going to do is choose the series, or the terms an equals 2, 1 over 2n minus 1. And so we'll use that, and bn, the comparison one, we'll just use that geometric series that we were dealing with, so 1 over 2n, like that. And now what we'll do is take the limit, so limit as n approaches infinity of an over bn, this equals to the limit as n approaches infinity, infinity of the an, there's 1 over 2n minus 1, put a bracket, all divided by this one right here, 1 over 2n. And simplify this further, what we can do is just write this as just simplified fractions. So right here, this is just writing as 1 over 2n, make this more spaced out, so we'll have 1 over 2 to the power of n minus 1. This one's going to be, well, divided by a fraction, so the bottom denominator gets on top. So what we'll have is a times it by 2n over 1, like that. So just get rid of those 1, simplify it further, and we'll have limit as n approaches infinity is going to be equal to 2n over 2n minus 1. And what I'll do now is divide both sides by the 2 to the power of n, or the highest power there, as I've done in my earlier videos on limits. So do this to multiply both sides by 1 over 2n, so we could simplify. This is going to equal to the limit as n approaches infinity, this one's going to cancel. It's going to be 1 over, now we're going to have this cancels 1, then minus, now we're going to have 1 times it by 1 over 2n. That's going to be, well, 1 over 2 to the power of n. So in other words, when we plug in n is approaching infinity, in this one we're going to get a 1 over infinity, which is approaching 0. So in other words, we're going to get a 1 over 1 minus 0. This equals to 1. Yeah, so it's a constant, and this is greater than 0. So yeah, we get the constant, this right here is equal to our c value, and this is going to be greater than 0, like that. So yes, that equals to 1, and yeah, since this limit exists, and it's greater than 0, and we're given, and we know that the summation 1 over 2n is a convergent geometric series, the given series converges by the limit comparison test. So yes, it's convergent. They're both convergent if there's the constant that we get, c is greater than 0. So let's go look further and look at now example 4, and this states, determine whether the following series converges or diverges, and we're given here the summation from n equals 1 to infinity of 2 times, you have 2 times n, actually we're dealing with n squared, not n cubed there. 2 times n squared plus 3n divided by square root of 5 plus n to the power of 5, like that. So let's go and look further here. So look at the solution. The solution states the dominant part of the numerator is 2n squared. So we have this 2n squared is the bigger part, bigger than the 3n, because remember we're dealing with going to infinity there. And the dominant part of the denominator is 5, or n to the power of 5 over 2, or square root of or square root of n to the power of 5. So the same thing as writing it like that. So yes, this suggests that, well, we'll just look at the dominant part. So instead of the 5, we'll deal with this n to the power of 5 all square root, and this 2n squared like that. So thus, this suggests taking, so I'll write right here an, let's write the equation that we're given, 2n squared plus 3n, like that, over square root of 5 plus n to the power 5. And then what we'll do is, and we'll write bn, this one we'll just take the dominant parts of the top and the bottom, because we're dealing with, again, infinity. As you get infinity, the larger ones are more impactful than just this 5 versus n to the power 5, or 3n versus 2n squared. So what we'll have is bn is equal to 2n squared over square root n to the power 5, and it's the same thing as writing n to the power of 5 over 2. So this is just square root like that. This just equals 2, and what I'll do is, to make it simplified, I'll write the denominator first, so n to the power of 5 over 2, and then we'll have let's try to make it the common denominator so we can combine the powers. So this is going to be 2n, and this is going to be a 4 over 2. So 4 over 2 is just 2. So now what we could do is, well, subtract this at the bottom there. So we can just, 5 minus 4 there. So we will have a 2n, and then 5 minus 4 is 1, so we'll have, this n goes away. This goes away, it's all gone at the bottom. So it's going to be n over 1/2. Yeah, so let's circle this, but recall this one, what it is. This is just a p-series. This just equals 2, or I'll just write equals to 2 times 1 over n 1/2, and this is a p-series. So recall p-series, let's go all the way above in my the comparison test, where the standard series that we use to compare. So here is a p-series, is the summation of 1 over n to the power of p, and converges if p is greater than 1, and diverges if p is less than or equal to 1. And this is going to be 1/2, that's going to be less than 1. So let's go over here. Scroll all the way bottom here. So this is a p-series. So I'll put this arrow after. So this is a p-series with p equals to 1/2, and this is going to be, well, less than or equal to 1. It's just less than 1. Alright, so just put less than 1. Thus, it's divergent. And I'll just put another arrow, second arrow, divergent series. So now we have a divergent series like that. So now what we could do is, well, this one's hard to compare with it, Yeah, it's hard to compare with it because, well, we have a 3n there at the top, and then there's a 5 there, and there's a giant square root. So yeah, but even in this case, it does look like this one is probably, this term is probably bigger than this term anyways. Just because there's a 3n that's pretty big on top, and the 5 isn't that big. So it should be divergent anyways. But nonetheless, we can use the limit comparison test to basically take the limit, and if it equals the constant c greater than 0, so yeah, so we could just take a limit. Right here, it's the limit again, n approaches infinity of an over bn equals c. If it equals c and it's greater than 0, then we can deduce that it is. Yeah, it is, because if this is divergent, they're both divergent. If it's convergent, they're both convergent. So let's look at it. So thus limit, so limit as n approaches infinity of an over bn, like that. This equals to, this equals to the limit as n approaches infinity, and then our an is going to be this over here. So 2n squared plus 3n, put like this, 2n squared plus 3n, divide this by, it's going to be a 5 plus n5. 5 plus n to the power 5 all square root, times it by, and then this one here we're dividing by bn, so divided by it, so the 2's goes to the bottom, this goes at the top, so we'll have a 2 and then an n 1/2. So now we have an n 1/2. What we can do is get the common denominator of the top and the top side there. So I'll just do that right here. So this n is going to be n to the power of 1. That's the same thing as writing 2 over 2. And this one right here, n to the power of 2, is the same thing as writing. So yes, this 2 is the same thing as writing, well, 4 over 2. 4 over 2 is just 2. So that we do that common denominator, so we have this 2. We can add these all up. So what we end up having is limit as n approaches infinity of this one, add these up, it's going to be 2n 5 over 2, and then plus here 3, and then this one added up, so n 3 over 2, like that. This is going to be all divided by, put the 2 in front, 2 square root 5 plus n 5. So now what we could do is, as I've done in my earlier videos on limits, we could do is divide this both top and bottom by the highest power. And in this case, n to the power of 5 over 2 is the same thing over here. N to the power of 5, then when you all square root, that's the same thing as 5 over 2, like that. So what I'll do is I'm going to write times it by, top and bottom by, or divide the top and bottom by n to the power of 5, the highest power, over 2. So when we're dealing with limits, you always want to deal with the most dominant terms as you go to infinity. So we have here 1 divided by 1 divided by n to the power of 5 over 2, and this one here is going to be 1 divided by n to the power of 5 over 2, so we don't change anything, because this same number divided itself is just 1. So we have that, and now what we're going to do is, multiply it all inside. We get a limit as n approaches infinity. Erase this. N approaches infinity. This one divided out is going to be, well, 2. These ones will just cancel. This one right here, 3n, and then 3n to the power of 3 over 2. So that's 3. We're going to just subtract the power, so 3 minus 5 is negative 2. So we'll have a plus 3n to the power of negative 2 over 2. Like that, which is just equal to negative 1, or 3 divided by n. And then right here, this is going to be 2 times, this one is the same thing as writing, square root. Yes, it's the same thing as writing. Well, that's going to be 1 divided by n to the power of 5 over 2. That's the same thing as just square rooting the whole thing there, and getting rid of that too. So n to the power of 5, like that. Times it by, here we have a 5 plus n to the power of 5. Now we can combine this inside the powers. Powers number is just power of 1 over 1/2. So this equals to limit as n approaches infinity of 2 plus 3, and this one's going to be, I'm just going to write this as, 3 over n, like that. This is just n to the power of negative 1, that's going to be 3 divided by n to the power of positive 1, like that. And this is going to be divided by 2 times, and then square root, then bring this inside. This one's going to be, well, a 5 over n to the power of 5, and then the n to the power of 5 just cancels and becomes 1. So now what we have is, well, limit as this goes to infinity, we have terms that we can actually know what's going on. So this one here is going to cancel. This is approaching a 3 over infinity. So this is approaching a 3 over infinity. I'll put it like that. Or what is it? So in other words, 3 over infinity, you're dividing by infinite large numbers, is going to approach 0. This one right here is approaching 5 over n to the power of 5. that's going to be approaching a 5 over infinity. So 5 divided by a large number is just approaching 0. So then what we have is a limit as this n approaches infinity. We're going to have a 2 plus a 0 divided by 2 square root. We're going to have a 0 plus a 1. So in other words, we're just going to get 2 over 2. And this 2 over 2, well, that's just equals to 1. Yeah, so this just equals to 1. And then this 1 is, well, we know that 1 is this equals to c, which is greater than 0. So that's the limit comparison test. And then we know this diverges, so this diverges, as I guessed initially, because that's a 3n there. And that's larger than this 5, so it's more impactful, and this is just getting larger, so this should be greater than that. So yes, my hunch was correct. Alright, so going further, so since this series Bn equals 2 times 1 over n and the power of 1 over 2, or square root n, is divergent, which is a p-series with p equals to 1/2, which is less than 1. The given series diverges by the limit comparison test, because this is a constant c that's greater than 0. So notice that in testing many series, we find a suitable comparison series Bn by keeping only the highest powers in the numerator and denominator. So yes, when you're dealing with limits to infinity, often the more dominant powers are the larger ones, or the ones that are more impactful on the actual result. So yes, those are good ways of finding series. So now let's look further. So estimating sums right here. So if we used the comparison test to show that a series An converges by comparison with a series Bn, then we may be able to estimate the sum by comparing remainders. So yes, if we know that they are, or if this series converges because this one's converges, then what we'll do is, well, we'll know that if we can find the remainder, as I showed in my earlier video how to do it on integral test and estimate of sums. So if we can find a numerical value for the remainder of the comparison series, which is easier, like the p-series or geometric series, then we can get an estimate for this entire sum right here, the an. So as in my earlier video on the integral test and estimate of sums, we consider the remainder. So where the remainder, we'll write this Rn. Remember, Rn is just equals to the actual sum, if it's convergent, minus the partial sum Sn, as however accurate you want to calculate it up to, and this just equals to the terms after this nth term. So we're going to have an An plus 1 plus An plus 2 plus An plus 3, and so on, plus ... And now for the comparison series Bn, we consider the corresponding remainder, and again we'll use the same notation as before, so we'll use now capital T. So Tn is equal to, well, this is going to be T, the actual sum, so this is the remainder, so of the comparison one, so lowercase t minus partial sum Tn, as however accurate you want to calculate up to. This just equals to, well, the remainder is going to be the remainder terms. That's going to be remainder terms after the one that you calculate up to. So Tn plus 1, Bn, because remember this is the B. B is the comparison one. And T is the total sum, Tn is partial sum. This one is, for S is the total sum, Sn partial sum of the An terms, like that. This is going to be plus Bn plus 2 plus Bn plus 3, and so on, like that. And now, since we're dealing with the comparison test, so we know that it's convergent by the comparison test, and then so that we'll have that as, since An, the terms are going to be less than or equal to the Bn terms for all n, then what we're going to have is that the remainder is also going to be less than the remainder here, because these terms are all less than it. So this terms, all of these terms are going to be less than this one, because again, we're assuming we used a comparison test. Hence, if we use the comparison test to show that this converges, because this is a convergent comparison series Bn, like that. Yeah, so this means all these terms are going to be less than all these terms. So yeah, so all the An terms less than all the Bn terms. So thus the remainder itself is going to be less than the remainder for the comparison term. So Rn is less than or equal to Tn. And if the series Bn is a p-series, we can estimate its remainder as in my earlier video, but replace Rn with Tn in the remainder estimate for the integral test. And again, here's recall from my earlier video on infinite sequence and series. So remainder estimate for the integral test. Yeah, this one's on the integral test and estimate of sums. So suppose f of k equals to ak. So this is, you can write it as a function where f is a continuous positive decreasing function for x is greater than or equal to n, and then the series an, or summation of an, is convergent. So if it's convergent, and we could write it as a function, if Rn, the remainder is equal to s minus Sn, then we'll have here. So the remainder is going to be in between, as I showed it before, in between the integral of f of x dx from n plus 1 to infinity. And it's going to be in between it. It's going to be greater than this one, and it's going to be less than from n to infinity of fx dx. So again, make sure to watch that video for more details. So if what we have here, so if the series Bn is a geometric series as opposed to P series, then Tn is the sum of a geometric series, and we can sum it exactly, because remember, the sum of a geometric series that's convergent is A over 1 minus R. And see exercises 3 and 4 at the end of this video, where I go over finding it, using geometric series. So in either case, we know that Rn is smaller than Tn. So let's look at example 5 to illustrate this. So example 5 says, use the sum of the first 100 terms to approximate the sum of the series. And then this is the series right here, summation from n equals 1 to infinity of 1 over n cubed plus 1. And then we're asked to estimate the error in this, or involved in this approximation. Alright, so let's look at the solution right here, and this one is, well, since we're given this one, so since we know that this term right here, 1 over n cubed plus 1, this is going to be less than, well, 1 over n cubed. Because again, you just have this extra 1, so you're dividing by a large number at all times, at every single term. So you're dividing by a large number, you're going to get a smaller number than without dividing by that extra plus 1. So we have 1 over n3. Remember, that's just a P series, and where P is greater than 1. Let's scroll up to what I wrote down earlier in the comparison test area. So P series, summation 1 over np, n to the power of p converges if p is greater than 1, diverges if p is less than or equal to 1. So again, from my earlier video on that. So that's p is greater than 1. So let's go back to it. So we have p is greater than 1. So this is a convergent P series with P is equal to 3 and that's greater than 1, hence convergent. So yes, so since this is the case, that's convergent and this is less than it, then the given series is convergent by the comparison test. So now going further, so the remainder Tn for the comparison series of this summation of 1 over n cubed was estimated in my earlier video using the remainder estimate for the integral test. So it was estimated in this video, but I'll just do that right now as well. So there we found that, that the Tn, the remainder is going to be less than or equal to the integral. So again, we're dealing with integrals right here. It's going to be less than n to the power of infinity of fx dx, like that. So here I'll write n to the infinity, and then our fx can be just 1 over x cubed, like that, dx. So again, using the integral test, or the remainder estimate with the integral test, or for the integral test. So what we have here is going to be now here we're going to write this as limit as t approaches infinity, just for this notation, because we're dealing with a limit there. We can't just take integral to infinity. So we take a limit, just use t, and this is going to be limit as t approaches infinity of this, and then this one here we can take the integral of this is, recall this one, the easy way to write is as x to the power of minus 3. So then what we'll do is take it or add a power. So we're going to have x minus 2, and then we're going to bring 1 down. Bring the negative 2 down. So it's going to be divided by negative 2 like this. So this is going to be our answer. This is from, let's write this a bit better. So this is going to be from x negative 2 over negative 2 from n to t, like that, as this is going to infinity. And again, this one here, if we take the derivative, we'll bring down the negative 2, these cancel, then we minus the power, so negative 3. So again, recall the derivative rules for power functions. And let's just take out this whole negative 2 there. And again, I went over this in my earlier video. So this whole thing, well, this right side equals 2, but then we'll just leave it there. So less than equal to, and just write this down. This is going to be negative 2, 1 over negative 2, just factor out that whole constant. So we could do this. Limit as t approaches infinity of, so take that out. And now what we have is a t like this. This is going to be t to the power of negative 2. Let's put this down like this. T squared like that. Then a minus Now we're going to have a 1 over n to 2. So yes, n to the power of negative 2 is going to be 1 over 2 like that. Or 1 over n to the n squared. So now that we have this, so we have this part right here. This is approaching, well, or this part at the bottom. This is approaching, or this whole thing is approaching. This is approaching 1 over infinity. So in other words, this is approaching 0. So what we end up having is, a negative 1 over 2 times by 0 minus 1 over n squared. So in other words, we're going to have the negatives cancel, so we're going to be left with here, this less than, so Tn is going to be less than, like here, Tn less than, this is going to be negative cancels, and we'll just be left with 1 over 2n squared. And I'll just circle this. So this is the remainder is going to be less than 2n, put a squared there. Yeah, so therefore the remainder Rn for the given series above, and that, because that's the comparison remainder. So remember, Rn is going to be, we're going to have Rn is going to be less than Tn. So we're going to have less than or equal to it. So that's what we have as the remainder. Rn is going to be less than or equal to, because remember that's the comparison one. This is Rn3. This one right here, where we're dealing with 1 over n cubed plus 1. So Rn is going to be less than or equal to Tn, which is less than or equal to 1 over n squared. Alright, so now with n equals 100, what we have is, well, 100 terms were asked for. So let's scroll all the way up here. So I'll sum up these terms afterwards. I'm just going to get the error first. So estimate the error involved in this. So we're going to have R100 is going to be less than or equal to 1 over 2 times 100 squared. So 100 squared, that's just going to be 1 over, let's just write this down. It's going to be 1 over 2 times, this can be 2 zeros, so we're going to add an extra 2 zeros, 100 squared, so 100 times 100, that's going to be 10,000. So we're going to have 2 times, we're going to have 20, and then we're going to have the zeros or have to match up, so we're going to have 1, 2, 3, so 20,000. And then what this is going to be is equal to, this is going to be, we're going to have, let's just do initially, if you have a 1, we're going to divide this out by 10,000 first, so we're going to have 4 zeros, so 1, 2, 3, 4. So in other words, we're going to have a decimal place here where the 1 goes from 1, 2, 3, 4. In other words, we're going to have a 0, 0, 0. Yeah, that's if we're dividing by 10,000, but then we're going to be dividing by an extra 2. So we're going to divide that in half as well. So a 1, 0 divided by 2 is equal to a 0, 5. Like that. So that's exactly this. And I'll just calculate it just to confirm my manual calculations, like that. And here's a calculation check. Again, my Microsoft OneNote application has built-in calculator, which is quite amazing, but it's not as, it doesn't go to that many decimal places. So calculation check number 1, 1 divided by 2 times 100 squared. This equals 2. I'll put, delete this, press equals, press space. Yeah, we get right there, 0.0001, 3 ones, which is rounded up because this is the exact one. So calculation check number 2, 1 divided by 100, 100 to the power of 3. This equals to, well, 0, 0. This is, this one is squared. I just put an extra 0 there. That's a calculation check like that. This equals to, so 0, which is rounded up. Yeah, so that's rounded up because it's not supposed to be 0. It's supposed to have another couple zeros there, actually. So going further, so what I did here is, so 1 divided by 100, this one's going to be correct because this is just 100 squared equals to, so it's exactly what I had there. So 3 zeros, because you're just moving the decimal places by 4 times, so 1, 2, 3, and 4, which is correct here, so which is right. Manual calculation check as I just did there, so 0.0001 divided by 2 equals to 4 zeros and a 5, which is right over that. Anyways, I just want to do that with OneNote, just because I want to. So using a spreadsheet, we can determine the partial sum S100, which is, the summation of 100 terms. So here's the Excel sheet. You can download it. Link will be in the description below as well. So term, we have, so 1, 2, 3, 4, all the way to, 10 to 100 there. You can play around with the Excel sheet if you want. So we have the terms 1 over n cubed plus 1, because you always have that extra 1, plus 1 there. So initially it's going to be 0.5, because you put a 1 in there, it's going to be 1 over 1 plus 1, 1 over 2, so 0.5. And then you add this up. So then the next terms will be 0.111. Then you can add those up, it would be 0.5 plus 0.111 equals to this. Then this one plus this term gets to this, and so on. And then when you sum these all up to I equals 1 to up to n, we get all the way up to here, 0.6864538. Yeah, so thus what we have is the summation from infinity, or n equals 1 to infinity, of right here 1 over n cubed plus 1 is going to be roughly equal to the summation from n equals to 1 of 100 up to 100 of 1 over n cubed plus 1, and this is equal to 0.68, or it's right, yeah, this equals to 68, or roughly equal to, yeah, 0.686453, like that. Yeah, and with error less than 0.0005. So yes, fascinating stuff. Alright, so now I'm done the segment, or the section in my calculus book, and now I'm going to go over 4 exercises that were referenced in this section, and I think it's very useful to go over. So exercises right here. The following 4 exercises are referenced in this section of my calculus book, so I thought it would be good to go over them too. So exercise 1 is over here, then I'm going to go over 4 exercises. So let's go over exercise 1 initially here. So it states, suppose that the summation, or the series AN and the series BN are series with positive terms, and we have BN is convergent. And here we're asked, prove that if the limit as n approaches infinity of the ratio AN over BN equals to 0. So this is the limited comparison test, except instead of just finding a constant greater than 0, here this is when it's equal to 0. So it proved that if we have this scenario, the limit of this ratio is equal to 0, then Bn is also, or then An, not Bn. So then Bn is also convergent if Bn is convergent, and this is the case. And then part B says, use part A to show that the following series converges, and we're given the 2 of these I, and this one is summation from n equals 1 to infinity of ln n over n to the power of 3. And then the second one, double I, the summation from n equals 1 to infinity of ln n over square root n times e to the power of n. Alright, so let's look at the solution. So for number A, or part A, so since we're given that the limit as n approaches infinity of the ratio an over bn equals to 0, yeah, then there is a number, capital N, greater than 0, such that, so the difference between this and the limit here, which is 0, alright, the absolute value of the distance, an over bn, minus this 0, so that's if it could be a different number, it would be just a different number. So it's going to be, it's going to be less than 1 for a specific number, for n is greater than capital N. Because remember, this is going to 0. Yeah, so this ratio is going to 0, so eventually as you get larger and larger, as n is approaching infinity, there's going to be a number greater than, a number where that the interval n is greater than this capital N, such that this is always going to be less than 1. Let's put that there, because all we need to do is just find any number here that's, just any number that we can do this, because as we're going to infinity, we can get any number. So you can make this as small as you can. It still can be satisfied because this is approaching 0 there, so it's approaching that limit. So when you take the difference from it, doesn't matter what that is, you can pick any number. So we're just going to pick 1 here, just to prove that this is the case, and it's going to be the case for everything. So for n is greater than capital N. And since an and bn are positive, then an is less than bn. In other words, here, so we have that's positive, just get rid of the 0, so an over bn, just put the 0 for completeness. This is going to be less than 1. Well, this is less than 1, but this is also right here, this is all, they're both positive terms, so we can get rid of the absolute value, so we can just have an over bn is less than 1, move the bn onto this side, so then we get an less than bn, like that. And yeah, so thus, since Bn, or the series summation of Bn converges, so does the series summation of An by the comparison test, because this is less than this convergent, or the terms of this convergent series. So every term is less than this one, so in other words, it's less than a converging series, so then this is convergent by the comparison test. So now let's look at part B, and it says use part A to show that the following series converges. And that's, let's look at the number I right here. So this is summation from n equals 1 to infinity of ln n over n cubed. So let's look at part B. So part B, and let's look at I right here. So I, we have the summation infinity n equals to 1 of ln n over n cubed. Yeah, so now what we could do here is, well, let's pick our an and bn. So our an is, I'm just going to write let an equals to ln, just a whole term, ln n over n cubed. And then here what my solutions manual does, it's pretty interesting. It checks here. So, I mean, it chooses bn equals to 1 over n squared instead of doing 1 over n cubed. Because if you have 1 over n cubed, then you're going to divide this by an divided by bn, then you're just going to cancel the n's. You're just going to have ln n. And the limit of that is going to go to infinity, which is not going to help. But if we have right like this instead, what we could have is something very, very interesting. And again, note here, this is a, this right here is just a convergent p-series. Convergent p-series where n is, with 2, p is equal to 2, which is greater than 1, hence it's convergent. So yes, we have, this is a convergent series, and now what we could do is take the limit as n approaches infinity of an over bn. Yeah, and then we'll see what we can get. So thus the limit as n approaches infinity of an over bn equals to the limit as n approaches infinity of ln n over n cubed, then divide this by bn, which is going to be divided by the numerator is going to go at the bottom, and the denominator is going to go at the top there, n squared like that. So now what we do is, well, this cancels with the 2, so yeah, this whole thing cancels. This is going to be left like that. So we're going to be left with equals to limit as n approaches infinity of ln n over n. But now what we have here is a scenario where we have, well, ln n, as n approaches infinity, this goes to infinity, and the bottom is going to infinity. So this is undefined. Yeah, it's undefined, but that's an infinity over infinity, and if you recall my early videos, I'll just write recall from my early videos the L'Hopital's rule. So L'Hopital or L'Hospital's rule, however you want to pronounce this, so L'Hopital's rule like this. I'm just going to put this in bubble. Like that. So just recall it, and I'm going to bring this down, and then recall, you could take the derivative of this. Whenever you have an infinity over 0 or 0 over 0, you can take a derivative, and you make sure to watch my earlier videos on that. So thus what we have is limit as, and here what I'm going to do is, yeah, so to use L'Hopital's rule, it's a function. This is just a series, so what I'll have to do is convert this over into just a regular function. So yeah, this is limit as n approaches infinity of ln n over n. This just equals to the same thing, because it doesn't matter if this is just integers, but then if you take any number, it's going to be the same thing as you approach infinity. So as n approaches infinity or as x approaches infinity, the same thing. So we're going to do ln x just for completeness sake right here. So ln x over x as this approaches infinity, and this equals to the limit as x approaches infinity of the derivative of the top and bottom. D over dx ln x over d over dx of x. Like that. So what do we end up getting is the derivative of the top. Well, recall derivative of ln x is 1 over x. So this equals to limit as x approaches infinity. This is going to be 1 over x. Then the bottom derivative of x is just 1. So like that. So we just get 1 over x. So limit as x approaches infinity is just of 1 over x. Yeah, that's just what we have. So in other words, as x approaches infinity here, we're going to get a 1 over infinity. In other words, we get a 0. So yes, 1 divided by a large number. I got 0. So hence, it's convergent. Yeah, so it's convergent. Also want to make another note here. This part right here, we got the ln x all the way to the derivative. My calculus book puts an h on top to indicate L'Hopital's rule. So let's put an h equals on top of the equal sign. So in other words, then we'll have L'Hopital's rule, and we can do it. So that's just a quick shorthand for it. So thus, what we have is the summation an, which equals to summation from n equals to 1 to infinity of the entire formula, ln n over n cubed. This converges because the Bn series is the P series that converges. So we have P, the convergent P series. We're dividing by it on the an. On the right here, limit as n approaches infinity of an over bn, it equals to 0, the whole thing. So that's what converges by this rule we just proved. So that then this is also convergent. So hence this converges by part A. Part A, like that. So yes, fascinating stuff. Alright, so now let's look at part II of part B. So scroll up here, so we get the part B, II. So this summation of n equals 1 to infinity of ln n divided by n squared times e to the n. So it's very interesting formula there. So let's just write this down. So summation from n equals 1 to infinity of ln n over square root n e to the n. So what we can do here is, well, let's just let an equals to just a whole function. So an equals to ln n over square root n en. And now what we know, well, one thing you should always note is whenever we're choosing the secondary or the comparison one, if we have a term that always can repeat itself, for example, here and bn, I'm going to choose this one, 1 over e to the n. And the reason is because this one, as you add these terms up, is just going to be 1 over e plus 1 over e squared plus 1 over e cubed and so on. In other words, we get a geometric series. And I'll show you this soon. So whenever you have something that keeps repeating itself in the powers, but everything else remains the same, we'll get a geometric series. So geometric series. So this is, I'll prove this soon, geometric series. And it's also convergent because you'll have 1 over e is going to be, 1 over e is going to equal to r. So geometric series right here. And I'll get to this after. Or I'll just write my hunch down and I'll prove it after. So geometric series r equals to 1 over e, which is, well, less than 1. And so then this is convergent. Convergent, and I'll prove this soon in more detail. So now that we have that, and what we can do is when we divide this out, this cancels, and we're going to have a scenario where we're going to have an infinity over infinity. So we have to apply L'Hopital's rule again. Yeah, so I just want to write that down. It's always good to see what answers you'll get before you're actually diving in. And then let's go here now. So limit as n approaches infinity of, then now we're going to have an an over a bn, like that. This equals to limit as n approaches infinity of ln n over square root n en times it by, this we're dividing by bn, so we're going to put the 1 at the bottom, en on the top, like that. So this cancels with this. So this is going to equal to limit as n approaches infinity of ln n over square root n. Yeah, so now this scenario again we're going to have, as I stated or alluded to earlier, just a few seconds ago. So we're going to have, as n approaches infinity here at the top and in the bottom, they're both approaching infinity. So we're going to have an infinity over infinity, so we can apply L'Hopital's rule. So what I'll do now here is, well, this equals to, I'll just write equals to, convert this into a function. I guess we're going to get the same thing when you take a limit as x or n approaches infinity. So as x approaches infinity of, I'll just put an arrow like this. It doesn't equal, it just approaches that. So we're going to have this limit as x approaches infinity of ln x, and we'll convert this into just a basic power, so x to the 1/2, so that's what the square root is. So now we're going to put that same notation I said above, equals with an h for L'Hopital's rule, and then this is going to be limit as x approaches infinity of d over dx ln x over d over dx of x 1/2, like that. Which equals to? Yeah, which equals to, let's just solve the derivative. So remember, ln x is 1 over x. So of limit as x approaches infinity of 1 over x, I'm just going to put it down like this, 1 over x, divide this by, now this one, we're going to bring the 1 over 2 down, then we're going to subtract the power. So minus 1 or 2 over 2, that's going to be, well, negative 1/2. So 1/2 minus 1 is going to be negative 1/2. So bring this above, but this make this all neat and tidy. So this is in the denominator, so we're dividing a fraction by a fraction, so then this denominator goes on the top. So what we're going to get is limit as x approaches infinity. And then we'll put the 2 on top, so we'll have a 2. Then this 1 over x is going to be, 1 over x. Put this 2 over x. And then this one right here, this is x to the negative 1/2. Let's make this on top. So we're going to have, or just leave it at the bottom. Let's just move it on top. So it's going to be x 1/2, like that, on the top. Let's move this. Times it by, just put this 1 x 1/2. And then now here what we could do is, well, subtract these powers. So this is 2 over 2. Yeah, 2 over 2. This is the whole number minus this. So we're just going to have 2 minus 1 is 1/2. So what we get is limit as x approaches infinity of 2 over, this is going to be, well, x is the power of 1/2. In other words, we'll get a square root of x. And then this one right here, as you plug in infinity, it just goes to 2 over infinity. In other words, it goes to 0. So there you go. We just proved it. Or I'll get to the proof. This is a geometric series. I'll prove that soon. Or I'll just prove that right now because, again, remember I said if it's repeating where the power is the only thing that's changing, it's usually geometric series. And whenever you have a 1 divided by a large number like that, it's going to be less than 1 there. So what we'll have is, so I'll write note that the summation bn is just equal to, and this is the summation like this. Summation from of n equals to 1 to infinity of 1 over en, and then if you sum these up, the first term is going to be 1 over e to the 1 plus 1 over e to the 2 plus 1 over e to the 3 plus dot dot dot. In other words, what we have is, well, we have a 1 over e, and then plus here we're going to have a over here 1 over e times 1 over e, which just gets 1 over e squared, plus here we're going to get a 1 over e times 1 over e squared plus dot dot dot. So yeah, so in other words what we get is, well, in geometric series terms, this is our a, and then what we have is over here plus here is going to be our a, and this is going to be our ratio r to the power of 1 there, and here you can also put r0 as times it by 1, like that. Let's put it in light dark there, and then plus 1 over e is going to be again a times it by r squared, like that, plus dot dot dot. So in other words we get geometric series right there. Yeah, so yes, thus this is a geometric series. So thus 1 over e to the power of n, the series is a geometric series with ratio r equals 1 over e, and hence convergent since the absolute value of r is less than 1. So yes, 1 divided by e, which is 2.718, etc. It's going to be a fraction less than 1. So yes, so that is a convergent geometric series. So thus the series an is converges by part a because bn is convergent. The series bn is convergent, and we have the ratio, the limit of this ratio, an over bn as n approaches infinity equals to 0. So yes, fascinating stuff. Alright, so now let's look at exercise 2, and it's pretty much the exact same as exercise 1, but now we're dealing with where the ratio approaches infinity instead of 0. So yes, fascinating stuff. So this is, again, the limited comparison test. So let's look at exercise 2, so part A. Suppose that the series an and bn are series with positive terms, and the summation bn is divergent. prove that if the limit as n approaches infinity of an over bn equals to infinity, so if this is true, then the summation an is also divergent. So if bn is divergent and the ratio an over bn approaches infinity, then an is also divergent. Then part B states, use part A to show that the following series diverge, and we're given I, so we're summation from n equals 2 to infinity of 1 over ln n. And again, the reason it's n over 2, just put a note, is because 1 over ln of 1, this just equals to 1 over ln of 0. In other words, we get a 1 over, ln 1 is equal to 0, yeah. So then we're going to get a 1 over, it's 1 over 0 is going to be infinity. So this is undefined, like that. So yes, so we'll just put n equals 2 instead. And then the second part right here is double I. So summation from n equals 1 to infinity of ln n over n. So let's look at now the solution. So for part A, let's just write this down. Since the limit, so we're given that the limit as n approaches infinity of the ratio an over bn equals to infinity, then when we're dealing with limits like this, then there is an integer capital N such that the ratio of an over bn, well, it's going to be greater than 1. We're going to have it a greater than 1, this ratio, because remember, this is approaching infinity. So there's going to be a point where it's going to be greater than 1. There's going to be a point where it's greater than 2. There's going to be a point where it's greater than 3. We just want to prove our point that this is also divergent. So what we're going to do is just make it greater than 1 whenever the term n gets to greater than this capital N. So there exists a number, capital N, such that this is the case. And essentially what we're doing is just taking the definition, this capital M equals 1 from my earlier video on the definition of infinite sequences approaching infinity, and my earlier video on infinite sequences, and here's from my infinite sequence video. There's Steemit notes on there, and also screenshot of the calculus notes right there, calculus book. So we have here, recall a definition of, so this right here, definition. So limit as n approaches infinity of an equals to infinity means that for every positive number, capital M, there is an integer capital N such that if n is greater than this capital N, the terms are greater than this capital N number, then an is greater than capital M, like that. So in other words, it could be anything, because remember, you're approaching infinity. This could be 100,000. It could be 100,000, but there's still going to be a number, capital N, such that as you approach infinity, that n greater than it will be greater than this number, because again, we're going to infinity. Infinity is pretty big. So thus for our case, what we have is an over bn is greater than 1, which equals to m in this scenario. So then what we could do is, well, this becomes, we move the bn on this side. So we get an greater than bn. And this is, again, whenever we have n greater than capital N. I got n period. So what we have is the terms here, an is bigger than the bn terms. But bn is a divergent series, so then we use the comparison test. So since the series bn is divergent, then an is also divergent by the comparison test, because the terms of an are bigger than terms of bn whenever n is greater than a certain number, capital N, like that, because remember, it's approaching infinity. So there it is, that's the proof. So now let's look at part B and part I of part B, or subpart. Part B, subpart A, I'll just put, I, and then part B, I, like that. So let's just look it up. So now what we're going to do is use this proof that we did, and then basically use this theorem to use part A to show that the following series diverges, which is, let's look at the first one here, I, which is the summation from n equals 2, because remember this is undefined otherwise, to infinity, and then of 1 over ln n. So let's write that down. So I'm just going to write that down. So the summation n equals to 2 of 1 over ln n up to infinity. So that's what we have. So what I'm going to do now is, first I'm going to just let's get it out of the way. Let's let an equals that term. So let an equals to 1 over ln n. Now for the comparison series, let bn, this is an interesting part of my calculus book. What they did was, well, what they picked is, because there's no series inside here that we could take, So all we have is ln n. But then the idea is we're going to take the ratio of an over bn. We want it to approach to infinity, and one way to always deal with this is, again, if we were dealing with limits to infinity, usually L'Hopital's rule is going to arise. So we want this the ratio such that we're going to have an infinity over infinity, or something like that. And also this derivative of ln n or ln x is going to be 1 over x. So we want some cancellations or whatnot, or just deal with similar terms. So what my calculus book did was picks cleverly bn equals to 1 over n, which is a harmonic series. So note that this is the harmonic series. And remember, the harmonic series is divergent. Harmonic series, hence it is divergent. Remember, harmonic series is just a divergent p series with p is equal to 1. So 1 over n power of p. So this one is going to be like that. So it's a divergent series like that. And recall the standard series that I illustrated way above here. The p series, again, just to double check. So the series, p series is the summation of 1 over n to the power of p. Converges if p is greater than 1, and diverges if p is less than or equal to 1. When it equals to 1, we get the harmonic series. So let's go back over to this. And again, for this a and bn, as I stated above here, it's undefined otherwise. So this is all for so I'll just put I'll just put it over here. For n is greater than or equal to 2. So we can't have it equal to 1 because it's not defined for our a n there. Alright, so that's what we could do is, so that's what we have is, so thus, when we take the limit, so limit as n approaches infinity of a n over bn equals to the limit as n approaches infinity of, well, a n is going to be 1 over ln n times it by, well, again, dividing by bn. So we're going to put the denominator at the bottom, the numerator at the bottom, and then the denominator at the top. Like that, just to flip it upside down when we're dividing by it. So now what we get is a limit as n approaches infinity of n over ln n. So as n approaches infinity, we're going to get a scenario again, and of infinity over ln n, like that. That's infinity as well. So of infinity over infinity, so we can apply L'Hopital's rule. So let's write this as a function. So this equals to limit, write this as x, because the limits are going to be the same. Limit as x over ln of x, which equals to, put an h on top for L'Hopital's rule. And then, yes, because it's pretty convenient actually, my calculus book does it. I've never done it until this video. So let's, going further. So L'Hopital's rule, so we take the derivative. Limit as x approaches infinity of d over dx of x, because we have infinity for infinity there. And then d over dx of ln x, like that. So now what we get is, alright, so let's just solve this these derivatives. So this equals to, limit as, I'll just fix this up, limit as x approaches infinity of 1 over x, like that. And then this is, the derivative of x is just 1. The bottom is going to be 1 over x. So 1 over x, like that. Yeah, so then this equals 2, the x just goes on top, and then we're going to get limit as x approaches infinity of x, which is just infinity. So in other words, what we have is, well, we have a divergent p series, or the harmonic series is the bn, and an divided by bn, the limit approaches infinity, and hence they're both divergent. Yeah, so thus, by part A, the summation an, which equals 2, summation up to infinity, n equals to 1, of 1 over ln n is divergent. Alright, so now we got that one's divergent. Let's look at part double I of this part B. So let's look at this series. So summation from n equals 1 to infinity of ln n over n. So let's write that down. So we have I, or double I, summation infinity n equals to 1 of ln n over n. So let's go back here, and again, this ln n over n, I believe it's going to be the third time that I've solved that it's divergent. I've done it already a couple times, once in this video and one in the previous one. So let's look at this one. So what I'm going to do is let, and we're just doing it a different way now. So let a n equals to, just the term that we're given, a ln n over n. And now this one's going to be easy to choose. The second one, so we're going to pick bn is equal to the harmonic series 1 over n. So in other words, we get the harmonic, similar as part I. So harmonic divergent series. Harmonic divergent series. Like that. Because p series with n with p equals 1. Alright, so let's go further, and now let's take the limit. So thus limit of the ratio n equals, n approaches infinity of a n over b n equals to limit as n approaches infinity of ln n over n, and then divided by bn. So we're going to put a 1 over, and then the denominator becomes a numerator, and so on. It becomes like that. This cancels with this. Yeah, so what we get is, well, this just equals to limit as n approaches infinity of ln n. In other words, this one approaches infinity. That's ln n. But my calculus book, it just becomes more technical and sets it to a function. But I believe you could do the same. So x approaches infinity. It's the same thing as writing limit as ln x. Limit as x approaches infinity of ln x, which equals to ln infinity is just infinity. So since bn is divergent and this ratio is equals infinity, then thus the other one is divergent. So thus the summation an, which equals to the summation of n equals to 1 to infinity of ln n over n, as again this is the third time that I've proved that it's divergent, diverges by part A, like that. So yeah, it's fascinating stuff. And also this shows that using different mathematical concepts can get to the same answer. For just solving the same problem in different ways. So it shows one of the remarkable feats of mathematics, or just basic logic written down in numerical form, which is math. So let's look at now exercise 3, and it states, use the sum of the first 10 terms to approximate the sum of the following series and estimate the error. And we're asked for this one right here. So the summation from n equals to 1 up to infinity of 1 over 2 to the power of n. Well, first thing we'll do is let's just sum up to 10 terms. So what we could do is, I'll write this as, so if we were to sum this up in a calculator, we'll have n equals to 1 up to 10, like this, of 1 over 1 plus 2n. This is going to equal to, when n is equal to 1, we get 1 plus 2 to the power of 1, plus 1 plus 2 to the power of 2, plus 1 plus 1 2 to the 3, plus dot dot dot, all the way to get up to 1 over 1 plus 2 to the 10. And now this equals to, well, 1 over 1 plus 2 is going to be 3, so 1 over 3. This one's going to be 2 squared is 4, so 5. Plus 1 is 5, so 1 over 5. Plus this one's going to be 2 to the 3 is 2 times 2 is 4 times 2 is 8. Plus 1 is 9. Plus dot dot dot. This one, in fact, is going to be 1, 0. Yeah, it's going to be 10 to 4 plus 1, so 10 to 5. And I'll do some calculation checks soon. If you plug this in a calculator, what you end up getting is 0.76352. Like that is what you get. And let's do some calculation checks right here. So 1 plus 2 to the 10. This is the erase. Just use the calculation check from my OneNote automatic calculator, which is quite amazing. So you plug that in and you get that answer. It's fascinating stuff. So now what we get is over here. So 1 divided by 1 plus 2 to the power of 1, and so on. And then to the power of 2, to the power of 3, power of 4, all the way to 10. What we end up getting is, let's just delete to show you that it's automatic, equals space, and there's a 5, so it's missing that 2 there. Let's just put a 2 and put an underscore, put an underscore like that, or underline like that, just because yeah, it's not as accurate as this one. So this one gets an extra decimal place like that. So yes, fascinating stuff. So yes, now going further, so we have this 1 plus 1 over 1 plus 2 to the n. So with comparison test, compare that with 1 over 2n. So since we have is 1 over 1 plus 2 to the n, this is going to be, well, less than 1 over 2n. Remember, this is just a geometric series. Remember what I said before? Anytime you have a number like this to the power of just the power of n, and then whereas you add the terms up, all you're doing is just adding another power to this. You're just going to get a geometric series like that. And this 1 over 1 plus 2n is going to be less than this one, because you're dividing it by just at every single term by a number greater than it at the denominator. You're just adding an extra term there, so you're dividing by a bigger number at each and every interval. So then you're going to be dividing by a large number, and hence get a smaller number at each interval. So yeah, since we have that, and as I showed earlier above about the remainder, so what we could do is if you look at the remainder for R10, which is this, remember R is for the this term, for the one we're looking at, for the AN series. This is going to be less than or equal to, because this is each term is less than this one. It's going to be less than or equal to the remainder of the T of 10 term. In other words, the BN series remainder. And this is going to be equal to, well, the remainder of this one is just going to be the summation from n equals to 11, because we're doing up to 10, so we're only looking at the remainder all the way to infinity. But this is, again, a geometric series, so we can calculate exactly this one. So instead of taking the integral as I did earlier, we could just exactly find this out. And this is by taking it from n equals 11 to infinity. So note, put note to show you that it's geometric series, as always. So the summation n equals to 11 to infinity of 1 over 2n. This equals to 1 over 2 to the power of 11 plus 1 over 2 to the 12. So the next one is 12. And then plus 1 over 2 to the 13, plus so on, dot, dot, dot. It keeps going on and on. This just equals to 1 over 2, 11, plus 1 over 2, 11, times it by 1 over 2, like that, plus 1 over 2 at 11, times it by 1 over 2 squared, and so on. Like that, keeps going on and on. In other words, what we get is plus a, which is this, plus a, which is this, times it by r. So this is a, times it by r, which is this, plus a, which is this, 1 over 211, times it by r. R squared, so that's this, and plus so on and on. And this is just a geometric series. And yeah, this power of 1, this power of r is 0 times by 1 is that, like that. So this is just a geometric series, like this, where a equals to 1 over 211, and r is equal to 1/2, which is, well, less than 1, as I showed before, hence convergent. So hence this is convergent. So hence convergent. So yes, fascinating stuff. Yeah, so now that this is a convergent, it's a convergent geometric series, we know that the formula for the exact sum of this, well, we know that. So in other words, what we have here is the remainder of this comparison series t to the 10 equals to, so this is the remainder of it, so we're looking at the sum from n equals to 11 up to infinity of this 1 over 2 tn. So that's what we have here. Yeah, so this equals to the geometric series. So we're going to do geometric series, and to infinity, we're going to write n equals to, well, we just put 1. Or just to avoid confusion, we'll just use a different term. So I'll write here as I equals to 1 of, from the I equals 1 up to infinity of a, and then r, instead of n minus 1, we'll just put I minus 1. So that's the, so right here, remember, if this is I is equal to 1, we're going to have R1 minus 1 is R0, and then there's a. Then we have, when I is 2, we have r2, we're going to have r to the power of 2 minus 1, which is 1. So we have a times 2 minus 1 is just a times r to the power of 1. So in other words, in this one, we call it the total of this. The exact sum of this is going to be a over 1 minus r. So in other words, this entire remainder is going to equal to a, which is 1 over 2 to the 11 over 1 minus, and then r, which is right here, 1/2, like that. So what we have here is, well, this equals 2. We could just 1 minus 1/2. That's just going to be, well, 2 over 2, common denominator. So it does 1 minus 1/2 is just a whole number, minus a half is just a half. Or 2 minus 1 is 1 over a common denominator of 2. So what we're going to get is, this just equals 2. Let's put all the way equals 2. 1 over 211 divided by 1 over 2. So I'm just going to move this 2 on top. So we get is a 1 over 211 times it by, move this over 1, and then this is going to be 2 on top. And this is 2 to the power of 1. We could just subtract these out, move it at the bottom. So this becomes 1 over 2 to the 10. Like that. Yeah, so that's the exact remainder of the comparison. Yeah, so thus what we have is we know that the remainder of this series, 1 plus 2 to the power of n, the remainder after 10 sub-intervals, or the partial sum of 10 intervals, the remainder after that is going to be less than or equal to the remainder of the comparison theorem, which equals to this. So thus, what we have is, thus, R10 is going to be less than or equal to T of 10, which equals to 1 over 2 to the power of 10 exactly. And this is roughly equal to, when you plug into the calculator, 0.00098 when you plug this in, like that. So there's circle it. So that is going to be the error. It's going to be less than that. Yeah, now to do a calculation check, this one again, as I showed before, it's not as fine-tuned. My OneNote calculator, built-in one. So I'll just use right here, DuckDuckGo. You can just search it there. So calculation check. Just type it in, 1 divided by 2 to the power of 10. It's going to equal to 0.0009765, and so etc. And this one, my solutions manual rounds up to 9. 8. So yes, so it is good. So now let's look at exercise 4 and the last one of this video, and it's again similar to exercise 3, and we're going to be dealing with a geometric series as well. So use the sum of the first 10 terms to approximate the sum of the following series and estimate the error. So yes, so let's go ahead and do so. So what we'll do is the summation up to 10, n equals to 1, up to 10 of n over n plus 1 power of 3n is equal to, so when we plug in 1, we're going to get a 1 over 1 plus 1, yeah, like that, 1 plus 1, and then 3 to the 1 plus 1 plus, that's going to be a 2 now, so 2 over 2 plus 1, 3 to the 2, and then plus all the way dot 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 all the way to 10, so we're going to have 10. And then we're going to have a 10 plus 1. This is going to be now a 3 to the 10. And let's get see what the first few terms are. So 1 over, this is going to be 1 plus 1 is 2 times 3 is 6. So 1 over 6 plus, this one's going to be a 2 over 3 times, 3 to the power of 2 is 9. So 3 times 9 is 27. And then plus dot 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 all the way to here. We're going to get in fact, we're going to get here is 10 over, yeah, right here, 10 plus 1 is 11 times 3 to the power of 10. Plugging out of the calculator, you're going to get a 649,539, like that. And then sum this all up. You're going to plug this all in the calculator. You're going to get a 0.2836, like that. And let's just box this out, like that. So it's going to be approximately that. That's to be the summation of the first 10 terms of this series. And now, like always, do a calculation check. So we'll do calculation check here. So we have 10 plus 1 just to get this 649,539. So 10 plus 1 times 3 to the power of 10. Let's just delete this and see what we get. Equals to, and there, yeah, there we get 649,539. And likewise here, now we sum this all up. So 1 over 1 plus 1 times 3 to the power of 1, and then plus 2 divided by 2 plus 1 times 3 to the power of 2, and 3, and there's 3's everywhere, 4's everywhere, all the way to 10. When we do sum this up, we get 0.2836, which is exactly that one. And also, since I don't have the solutions manual for this particular exercise, yeah, I had to do it myself. I have double checked the calculation using the same spreadsheet from earlier, just to double check the numbers are correct. Before I would use this calculator, this built-in one in OneNote, to confirm that the calculus book is right. But now there is no solutions, so I had to check if my number right here was correct, or if I made a mistake somewhere here. So use Excel sheet like this, and use Excel as terms 1 all the way to 10. There's each term. 0.166 is the first one. Yeah, so 1 divided by 6. And then here, add these up all the way up here. So sum these up to partial sum. So this one, so this plus this, so this equals to this. And then when you add this to it, you get this number. And then this, add these up, you get this one. In other words, sum of this one is equal to this, sum of this equals to this, and so on. All the way there, so sum all these up together gets this 0.283569. So in other words, rounded up 0.2836. So exactly correct. Alright, so now what we could do is try to find the error. So we have that sum. So what we could do is let's look at this one again. So n over n plus 1, 3n. So we have, yeah, so I'll write, since, I'll just write this whole thing, n over n plus 1. Yeah, so since n, I'll actually write this afterwards. So what I'll do is write, since n over n plus 1, this is going to be, well, less than n over n. Because here we're dividing by an extra plus 1 there, so we're dividing by a larger number, so this is going to be less than where this equals to 1. So thus, what we have is the entire terms n over n plus 1 times 3n. So this whole scenario is going to be less than n over n. Yeah, so this is going to be less than 1. Times it by this divided by this 3n. So in other words, there's going to be a fraction timesing that. Yeah, so in other words, what we're going to get is, well, this is going to be less than, I'll just put this, yeah, so down, this is just going to be less than n over n times 3n. In other words, this just equals to, yeah, 1 over 3n. So in other words, this is going to be less than 1 over 3n. And this is another geometric series, because remember, this is just going to be, when you add these up, all that changes the power, so it's going to be 1 over 3 plus 1 over 3 squared plus 1 over 3, etc. And then 1 over 3 is r is less than 1, so it's going to be convergent geometric series. Yeah, so since it's less than it, so then as I stated earlier, so thus the error is R10 going to be, yes, the remainder is going to be the error R10, which is less than the remainder of the comparison theorem T sub n less than or equal to of the summation, like this, of n equals to 1 or from n equals to, from n equals to 11 up to infinity. Because remember, it's a remainder after that, so we're going to be summing up. We can do exactly, so 3 to the n, like that. Where this is again a geometric series, like this. I'll just do this for completeness sake, draw this all out again. So note that summation infinity from n equals to 11 up to infinity of 1 over 3n, this just equals to 1 over 311 plus 1 over 311 times it by 1 over 3 plus 1 over 311 times it by 1 over 3 squared, etc., etc. So all the way, keep going on and on. So yes, this is going to be 1 over 3 power of 12 and so on. So this is going to be a, which is that term, plus a, which is that term, times it by r, which is this term, 1 over 3, plus a, which is this term, times it by r, which is r squared, and so on, where this is going to be r0 times by 1, like that. So there it is. Yeah, so that's what we have. As always, just for completeness sake, always write it down, so you should be able to do this all in your head without even having to write this down. So geometric series, so thus we have a geometric series with a equals to 1 over 311 and r equals to 1 over 3, which is less than 1, hence divergent. Yeah, convergent, not divergent. Convergent. Like that. Yeah, so thus what we have is we can get the exact formula or exact amount of the remainder of the comparison theorem. So thus T of 10 is equal to summation n equals to 11 up to infinity of 1 over 3n, which equals to, and again change the variable to I just to avoid confusion. So up to infinity, I equals to 1 of a times by r I minus 1. So again, the geometric series, this is going to be equal to 1 over AR, the exact sum, as I showed in my earlier video, and as I recalled earlier in this video. So this is going to equal to A, which is 1 over 311, divided by 1 minus 1 over 3. And now this number right here, 1 over 311, this one right here, divided by 1 minus 1 over 3. This is going to be, well, 3 over 3, so 3 minus 1 is 2. So in other words, we're going to get 1 over 311, 1 divided by 1 minus a third is going to get 2/3. So 2/3, so we can move the denominator on the top because we're dividing by this out. So 1 over 311 times it by 2, times it by 3 over 2. So we're going to get is 1/2 times it by, and here we're going to add the powers or subtract the powers because they're divided by. So we're going to get is times it by 1 over 311, 310. So this is the exact value of the remainder that we get of the comparison theorem. So thus what we have is R10, the error, is going to be less than or equal to the R10 of T10, which is the comparison remainder or the error, and which is equal to exactly 1 over 2 times 1 over 3 to the power of 10, which is approximately equal to, and if you plug in the calculator, you get a very, very small number, and this is more exact than mine, so more exact than my OneNote calculator. So we get 0.000, I believe there is 6 zeros, so that's 4, 5, 6, and then 8, 4, 7, actually there's 5 zeros. 0, so 5 like that, 8, 4, 7. So circle this one like that. And now, yeah, so calculation check, again, it's more, it's too fine-tuned for my calculator with the OneNote, so I just use DuckDuckGo, so search it up. So 1 over 2 times it by, so when I plug it in, I don't know why it's a 1 there. But anyways, 1 over 2 divided by 3 to the power of 10. So that's what we get there. So 1 over 2, times it by 1 divided by 3 over 10, or just 1 over 2 divided by 3 to the power of 10. And we get, this is 5 zeros, so 0.000008467, and here's rounded up to 7, so 847. So yes, again, as I stated, there's no solutions manual for this one, but I'm pretty sure this is right. If you want, double check and let me know if I got it right. Anyways, that is all for today. Hopefully you'll learn from this. Another epic long video, and I'll be going over more infinite sequence series later, and hopefully you like this kind of format where I go through a whole section, as many hours as it takes just to get it done, just because I got a lot of other work to do, a lot of other gyro experiments if you've been following. It's pretty epic. So anyways, that's all for today. Let me just scroll all the way up. And like always, you can download these exact notes in the link in the description below in PDF format, and also on Steemit. You can view these notes on Steemit. The link will be in the description below in article format. Anyway, that's all for today. Thanks for watching, and stay tuned for another Math Easy solution.